Hi there, welcome back to a new recording. This is Jihad Hamasai, the high school chemistry teacher. In today's recording, I'll be explaining the enthalpy changes in chemical reactions. At the beginning of the session, I'll be introducing the enthalpy, and then we'll be talking about the dependence factors which affects the enthalpy, and then we'll be talking about how to solve the enthalpy through the Hess's law, and then by using the equations. At the end of the session, we will be solving some of the Ministry of Exam questions. Let us start with the introduction about the enthalpy, guys, first. Of course, the enthalpy in reactions refer to any changes, whether it's a physical or chemical reactions in chemistry. When there will be a process, there will be change in the heat of the reaction. There will be change in the heat of the reaction. Whether the process, to process, it needs to add heat, or in order to process the reaction during the processing, it releases heat to the surrounding. That heat here we call as the enthalpy. So it represents the total heat content of a system at constant pressure. In a system, the system, we mean the reactions, can be two types, exo and endo. Later we will be defining those types of reactions, guys. The absolute enthalpy cannot be measured direct. Guys, we are not able to measure enthalpy at a specific point during a path of reaction. Why? Because enthalpy is a state function. A state function, we mean it depends on the 2 pointers, the initial point and the final point. At the beginning of the reaction, we should measure the heat of the system, and at the end we should measure the heat again, and then subtract the initial from the final to result the enthalpy change of the reaction. So the enthalpy change can be calculated rather than enthalpy at a specific point, and quantifies heat absorbed or released during a process. So the enthalpy change can be the amount of heat that released in a process, or amount of heat that absorbed by a reaction. And to solve the enthalpy change, of course, we should subtract the reactant's enthalpy from the product's enthalpy. We mean at the beginning of the reaction, the reactant, we should measure how much heat do we have in the system. And at the final point, at the end of the reaction, we should measure the heat and subtract the beginning from the final, the initial from the final. That will result the enthalpy change of the process. For the reactions, guys, we have got two types of reaction in terms of releasing or absorbing heat: the exothermic and then the endothermic reactions, guys. What are the differences between the endo and exo? The main difference is the direction of the energy, guys. From the exothermic, the process is going to release heat to the surrounding, but in endothermic, the heat flow to the system. We should add heat to the system, the system absorb heat in order to process. And in terms of signs, guys, the sign of the enthalpy when it's exothermic should be less than 0. We mean negative signs. And then if it is endothermic, we add heat to the system, it should be more than 0 or positive sign. The temperature, guys, of course, what will happen to the surrounding when a reaction is exothermic? It warms up the surrounding because it releases a high amount of energy to its surrounding. But in the endothermic, it's just the opposite. It cools down the surrounding environment of the system. When we have a reaction in a specific container like a beaker, guys, through the exothermic we can touch the beaker and then feel if it's hot, exothermic. If it becomes colder, it becomes an endothermic process. To represent the paths of reactions, it's very important to know what's going on during the exothermic path of reaction or during the exothermic and endothermic paths, guys. As you can see, this path shows the exothermic reaction pathway. In exothermic reaction, we should know the position of reactants and product. Guys, the graph represents two lines. The vertical line represents the enthalpy change, and then the vertical line represents the course of reaction, or we can say time. As the time process, what will happen to the change in enthalpy? So guys, the exothermic reactions, we mean releasing heat in a system. That means the initial position, which is the reactant, we have a high amount of heat, but till we reach to the product, it's going to be released this heat. What will happen to the final position? Of course, it should be always lower than the initial position, which is the product. So what's important about the path of exothermic? We should know that enthalpy of product, or we can say enthalpy of reactant, is always higher than the enthalpy of the product. And guys, if we want to calculate the enthalpy change, we will get a negative value. Suppose this is a 50 kilojoule and that one 100 kilojoule, guys, or 150 kilojoule. Let us calculate hypothetically, through using those values, what will be the result of the enthalpy change. Enthalpy change is equal to what? The product minus the reactant. What's the product position energy? It's 50. Minus the reactant position energy, it's 150. So results what? Minus 100 kilojoules. That's how we should know that always exothermic has a negative enthalpy. In terms of stability, guys, there is a term we call a stability related to enthalpy. The stability is inversely with the enthalpy, guys. And a system that has a high energy, that means it's unstable. The systems with low energy, they are what? Stable. So which position is in lower energy position here? The product. So we can say simply product is more stable. Is more stable than the reactant because of having a lower energy state than the reactant. And then the same procedure we can show for the endothermic course of reaction, which is the opposite just. In endothermic course, guys, in the reactant is in a position of energy, but to reach to the product, we should add more heat in order to process the reaction. Addition of the more heat, that means the final position will be in a position of energy with a higher heat, and then the product will be in a higher position of heat than the reactants. So the reactants here, they are in a lower position of heat than the product. As we can see that here, suppose it's 50 and then the above is 150. So let us determine the enthalpy change, which is the product 150 minus the 50 results a positive enthalpy, which is 100 kilojoules. So for endothermic, always the enthalpy change should be a positive value or more than 0. And which position the reactant or the product is more stable? Of course, here the reactant is in a lower position of energy. That's why the reactant is what? Is more stable. The stability works opposite to the enthalpy change, guys. Don't forget that. In enthalpy changes, we should write the equations in a way we call as a thermochemical equations, guys. So let us define what's a thermochemical equation and how to write a thermochemical equation and how to measure whether a reaction is indo and exo through the thermochemical equations. Simply, a thermochemical equation is an equation that quantities of energy released or absorbed must be represented. So when we write an equation, if there will be an amount of energy represented, there are two representations we'll be talking about. That means it's a thermochemical equation. An equation that represents the heat of the reaction. Must include the physical states of reactant and product, because in a thermochemical equation, if we change the reactants and products status, that's gonna change the enthalpy change. And also shows energy flow as heat. We should be using the thermochemical equation to indicate whether it's an exothermic process or endothermic process. We'll be reading that. An enthalpy change indicates direction of energy flow in the equations, guys. So we have two ways in order to read the enthalpy through the thermochemical equations to determine whether it's exothermic or endothermic, guys. If the amount of energy is given within the equation, it's in the reactant, okay, that means it's always indo. Which direction is indo? Forward. How about the reverse? The reverse is exo. If the amount of it is written in the reactant, the forward indo, the reverse exo. But if the amount of heat, the same equation, O2 plus C, okay, CO plus 393.5, it's written in the product side, that means it's what? The forward is exo, and then the reverse is indo. So simply, this is the first way. If the energy is written within the equation, in the reactant, its forward is indo. If the energy is written in the product, the reverse is indo, and the forward is exo. So the energy here is written in the reactant, the forward is indo. But if the energy is written in the product, the forward is exo, and then the reverse is indo. The second way is given as enthalpy change, guys, to us. If it's given at delta H, we should determine through the sign. If it's negative, that means it's exo. But if it's positive, delta H is equal to a positive value, that means it's indo. So these are the two ways we can determine the endothermic and exothermic processes through the thermochemical equations, guys. The rules for thermochemical equations, or the factors that changes the enthalpy change. Guys, a thermochemical equation, as we define it, that is an equation includes the amount of energy released or absorbed in a process. It can be physical or chemical processes, doesn't matter. What are the factors that affects on the enthalpy change? First of all, the physical state. Of course, changing the physical state, liquid, gas, aqueous, and then a solid, that gonna change, influence the energy change, guys. As we start, the evaporating water with liquid needs less energy than evaporating solid liquid. Because solid liquid should be liquefied first, we need an additional energy to liquefy it, to melt it somehow, and then evaporate it. To the gas, we need another energy. So changing the status gonna change the enthalpy change. This is first. The second one, stoichiometric relationships, guys. The amounts. As we change the amount of reactants and products, that gonna change the amount of the energy as well. So the coefficient in a balanced equation represents not only reactant and product ratio, but also energy changes. The coefficients, the amounts, the moles, they're gonna affect on the enthalpy change. As the coefficient they increase, they're gonna increase the enthalpy change. As the coefficient decrease, they decrease the enthalpy change. The reverse reactions, guys. When we reverse the reaction, the sign of enthalpy reverses. You should know that. When we reverse a reaction, if forward is positive, so when we reverse it, it's gonna be negative, or vice versa. And always, if the forward direction is a process, the reverse direction will be the opposite process. An example, if the forward is exo, the reverse will be the indo. Multiplication and division, guys. This works on the coefficients, the moles. As we multiply the reaction by a factor that should be multiplied, the enthalpy should be multiplied by the same factor, the same number, the same amount. Or divide the reaction by a factor, a number, we should divide the whole enthalpy by that number. So as you can see here in this reaction, the enthalpy change is 241.8 kilojoules. We multiply the reactions by 4, so the reaction becomes what? The reaction enthalpy should be multiplied by 4 as well. Okay, it's gonna be 4. Of course, the above equation should be 2 and 2 for balanced equation, and then we multiply by 4, multiply by 2 to be 4. So it's gonna be 4, 2, 4. So this should be multiplied by 4 as well. But this reaction should be a little bit edited. When we multiply by 2, we'll be getting 2 to 4 multiplied by 2. This multiplied by 2, this should be 2, of course. If you multiply by 4, that will be 8, 4, 8, and then this should be multiplied by 4 as well. So what I mean, the concept is what? When we multiply the reaction by a specific number or divide, you should apply the same factor for the enthalpy change. The last effective factors that affects the enthalpy change is what? Is pressure or temperature. Guys, the enthalpy changes by pressure. We should always measure the enthalpy change as a constant pressure. As the pressure changes, that's gonna change the enthalpy change. But the temperature is not significantly affected by or affects on the enthalpy. So the temperature is not the one of the factors that affects on the enthalpy change, but the pressure changes the enthalpy. Here we have got the types of enthalpy. There are 3 types of enthalpy: enthalpy of reaction, formation, and then combustion, guys. Let us talk about what's the enthalpy of the reaction, and then we'll be talking about formation and then combustion as well. The enthalpy of reaction is the overall change in the enthalpy during a chemical reaction. This can be calculated for any reaction without any restriction, without any conditions, and has a unit of kilojoule. Enthalpy of reaction. It represents by delta H with the this small circle we call as the standard state of because we should measure the enthalpy at the standard states of the reactions. Quantifies heat absorbed or released. We should be knowing that the delta H can be exo or endo. Specific to a balanced chemical equation is a specific for the specific amounts, can be changed for different amounts. Proportional to stoichiometric amounts that can be changed directly proportional to the amounts. As the amount increase, enthalpy change increases. As the amount decreases, enthalpy change decreases. How about the enthalpy of formation, guys? The enthalpy of formation has conditions. It's not such as the enthalpy of reaction. Both formation and combustion, they have their own conditions. Said whenever 1 mole of a compound formed from the elements. Two conditions. 1 mole of a compound from the reaction of the elements. That we can say that the enthalpy of formation, and then its unit is what? Kilojoule per mole. It should be the standard conditions of pressure and then temperature. Delta HF at the standard state for the elements in their natural nature is 0, guys. You should know that the delta HF for the elements is 0. Use it to calculate reaction enthalpies, but when 1 mole of the compound formed from the elements. Here we have got examples. The first one, guys, it's the 1 mole of CO2 formed from this carbon and oxygen. So these are the elements. That's the 1 mole of the compound. So simply we can say that delta HF of the reaction is equal to that amount. But for the second equation, have a look. 1 mole of the compound formed, but is that from the elements or from one compound and the other element combust with the oxygen? So the elements are not, CO is not element. That's why the delta H can be written delta H of the reaction, not delta HF. So in this, the second equation, delta H of the reaction is not equal to the delta HF because it has only one of the conditions. It does not meet the second conditions, which is it must be obtained from the elements. And the last type of the enthalpy, which is the enthalpy of combustion, it has two other conditions. 1 mole of an element or compound combust with oxygen. Enthalpy change when 1 mole combust with an excess oxygen amount, and probably usually with the highest amount of oxygen, and it's measured in a unit of kilojoule per mole, guys. Usually it's negative, but except the case of combustion of nitrogen. Combustion of nitrogen is exceptional when it's not exothermic, it's endothermic. Complete combustion must be occurred. How complete combustion? We mean highest amount of oxygen should be used in order to be complete. 1 mole of the reactant must be reacted with the oxygen. And then, of course, we should measure at the standard conditions. When the fuel combust, with the oxygen, produce the products, usually CO2 and H2O. Guys, let us provide examples. 1 mole of carbon reacts with oxygen, so that's the delta HC of the carbon is equal to this amount. Why we call delta HC? Delta HC refers to the enthalpy of the combustion at the standard states. Why? Because 1 mole of the carbon combusts with the oxygen. Here, the next example, carbon monoxide. 1 mole, it's an example for the compounds. Unlike the formation, which the compound should not be in the reactant side, should be in the product. 1 mole of the compound formed from the elements. Here the compound can be combusted, element or compound, both they can be combusted with oxygen to form the CO2. This is delta HC, which is equals to delta H of the reaction, guys. The conditions which the delta H cannot be equal to the delta H when there is no oxygen. For example, if H2 reacts with the I2 form 2HI. In this reaction, guys, we have got H2 reacts with I2. There is no oxygen, so the oxygen is not in the reaction. That's why it's not combustion process. Another example can be provided as more than 1 mole reactors. For example, 2H2 plus O2 form 2H2O. This is delta HF. Delta HC is not equal to the delta H. Why? Because 2 moles of oxygen combusted. How to convert this to be delta HC equals to the delta H? of the reaction, we should divide by 2 to let the mole, the coefficient of the hydrogen, to be 1. So simply that was the enthalpy types, guys. We have got one note in this part. When the enthalpy of the all the enthalpies will be equal. That note is important to be stated, guys. I'll be stating here the note. The enthalpy of the enthalpy types will be equal when 1 mole of a compound, for example CO2, formed from the combustion of 1 mole of its element with the oxygen. For example, this example, if 1 mole of the compound formed in product by the combustion of 1 mole of its element with oxygen, that's the what all the enthalpies are equal. Delta H equals delta HF equals delta HC. Another example, when H2 reacts with the half O2 to form H2O. Okay, 1 mole of the compound formed from the combustion of 1 mole of its element with oxygen, thus all the enthalpies are equal. Let us try to talk about how to measure the enthalpies, guys. There are 2 ways to measure the enthalpies. The first one is by using the formula. The formula is given here, but the formula can be used when we have got the enthalpy formations of reactants and product substances, guys. Usually we multiply the N, which is the amount of the the reactants and product in mole, the coefficients, multiply the delta HF of the products minus the M, which is the coefficients of the reactants, multiply delta HF of the reactants. So the delta H RxN, standard enthalpy of reaction, represents that symbol represents the summation of the all enthalpies, and N and M are the coefficients. Delta HF is the standard enthalpy of formation, guys. We should know that we do not forget that the standard enthalpy of formation for the elements in their standard states is 0, and then enthalpy is a state function, so the path does not matter. We need to measure the final and the initial enthalpies to calculate it. Let us calculate the combustion of methane, guys. Here the methane combusted to form CO2 and H2O. First of all, let us balance the equation. Is that balanced or not? One carbon for hydrogen, for oxygen. That's the balanced equation, guys. The oxygen is elementous, so it's 0. We can cancel this as it's given is 0. The enthalpy formation for the CO2 is given to us, which is this value, and then H2O is given, and then methane is given. So how to calculate that? The product enthalpy of formations, multiply their moles minus the reactant, multiply their mole. For the CO2, it has got minus 393.5, multiply 1 because its coefficient is 1, plus what other compounds do we have in the product? H2O. H2O, it has got 2 mole, 2 multiply its enthalpy of formation, and then this is the product, minus, that's the minus in the equation, minus what? The enthalpy of formation of the reactant, which is the methane. Methane is minus 74.8, multiplied by 1. Why? Because it has a 1 mole as a coefficient, and 2 multiplied by 0, we will cancel this because the coefficient is 2 but its enthalpy of formation is 0. That's why we do not count it. That's the enthalpy of the reaction through the enthalpy of the formation. We can calculate it. And the second way is by using the Hess's law, guys. Hess's law talks about the total enthalpy of the steps in a process. When we add all the enthalpies of the steps, results the enthalpy of the reaction, guys. Of course, enthalpy is a state function. You know that overall enthalpy change is constant. The overall enthalpy change is constant for specific conditions of temperature, pressure, and then amounts of reactants and product with physical status, guys. Do not forget, when we talk about the Hess's law, where in addition of the Steps, we should know that when we reverse a step, we should reverse its enthalpy, as this one is A goes to B is minus 200, but B goes to A, it becomes 200 positive. Or when we multiply or divide the reaction by a factor, we should multiply or divide the enthalpy by the same factor. As you can see here, we multiplied the reaction by 2. Okay, 2 multiplied by 1 equals 2, 2 multiplied by 3 6, 2 multiplied by 2 4, and then we should multiply the enthalpy by 2 as well. 92 multiplied by 2 is 184, minus 184. So the total enthalpy of a process equals the summation of the enthalpy of the steps. Path 1, path 2, path 3, they're all results the enthalpy overall. Guys, examples for finding the enthalpy by using the Hess's law can be used, or by using the equation. Some of the example we can use just Hess's law. Some of the example we can use the enthalpy equations. Why? Because if there will not be enthalpy formation, we cannot use the equations, guys. Okay, let us solve these examples. Here it's given that the enthalpy of this reaction should be calculated, and then 2 steps are given to us. Of course, guys, always keep in mind that except the oxygen in the reactions, how many reactants and products there will be in the reaction, there should be the same amount, the same number of the steps. Okay, guys, we should check for 2 things, guys. The steps, check the steps to 2 things based on the overall reaction. This is the overall reaction which is the required. The substance in the step should be the same side as the substance in the overall, and then with the same coefficient. For example, except the oxygen, because oxygen repeated in all the steps. What do we have in the step, in the overall? Carbon. Carbon exists in which step? Here, this step. Is in which side in the overall? Reactant. Is that in the reactant in the step? Yes, so do not change it. If it was in product, we should reverse it to be the same position. And if it is, what's the mole in the main equation? It's 1. So in the step is 1. If it was not 1, we should change into 1. Okay, so rewrite the first step the same and change it. The second one, CO2. CO2. Where is the CO2? In product, in the main equation. In the step is in the product. So 1 mole in the product, 1 mole. No, stay and change. So add them together, you'll get the enthalpy change of the above equation without any changing. So let us solve the second example, guys. As you can see, this is the result, or the enthalpy of formations are given. That's why we can calculate or use the equation as well. That was the Hess's law which I used. For this reaction, 2 steps are given, guys. We should be checking for the, do not check for Cl, because Cl is repeated. Usually the element which is repeated in all the steps, do not change or reverse or multiply or divide the steps based on that element. Try to see the other elements. Fe exists in which step? The first step. So in the main equation, Fe is in the reactant. Here is in the reactant. 1 mole, 1 mole. So unchanged. Rewrite unchanged. FeCl3 is in the main equation. FeCl3 is in this step. In the product in the main equation, 1 mole. In the product, 1 mole. So stay unchanged as well. Add them together, you'll get the enthalpy of the above equation. So the Hess's law, the principle of Hess's law, we should change the steps for 2 things. One, the species in the main equation is situated in which side? In the step, it should be in that side. If it's not, we should reverse it. As we reverse the reaction, the sign of the enthalpy should be reversed. And then if the mole is not the same mole, you should change for the moles by multiplying or dividing, guys. Let us solve this question by using the delta HF and then the other equation by using Hess's law. Guys, here we have got the oxygen is 0. You should know that 0 is given. SO3 in the product, so the enthalpy of SO3 is given to us, but multiplied by 2 because its coefficient is 2. 2 multiply minus 395.7 minus from the equation SO2, which is but the coefficient is 2 as well. 2 multiply minus 296.8. That can be used, you can use the equation, the calculator, to solve the results. That's the procedure. I'm going to talk about the procedure because to not let the video to be I mean a long video. Shortly, that was the procedure. Okay guys, let us solve the other equation, solve the enthalpy by using Hess's law. As you know that three steps should be given because there are 3 substances. Okay, let us solve the question by checking the positions of those substances and the moles. As you can see in this reaction, guys, the carbon is in the reactant, and the first step carbon is in reactant. 1 mole, 1 mole. So we write carbon the same. The second in the equation, the main equation is that equation that the enthalpy of reaction is the required. The 2 mole of H2 is given, but here 1 mole. So you should multiply this by 2. Just multiply by 2. Does it has the same location? I mean the same position, reactant? Yes. This third step, methane is in the product, but in the third step methane is in the reactant. 1 mole, 1 mole. So we should be reversing that. Okay, we should be reversing that. When you reverse it, it becomes positive. It's negative, becomes positive. And then add the enthalpies, results the enthalpy of the above equation, guys. There are another type of questions to find the enthalpy through the graphs, guys. How to do that? Here we have got this equation said it's unknown. By using those above steps, which the enthalpies are not given, how to find the unknown enthalpy. Of course, we should use this method. We should find the reactants of the first step on which one of the lines, those red lines, energy lines, and then the product on the other line, and then in between those 2 lines we should measure the enthalpy change. So carbon and oxygen is on the first line, second and third line, and then CO2 is on the third line. So between the 0 to minus 393.5, it's what? It's minus 393.5. So the delta HF for the step 1 is minus 393.5 kilojoule. And the second one, carbon and half oxygen, situated on which energy line, guys? Carbon and half oxygen on the second energy line till the product CO2. So till the product, this is minus 283 kilojoules. Now, how to use this to find the unknown enthalpy? Of course, we should know that the carbon in the first step, second step, carbon is in the first step, in the overall is in the reactant, in the step is in the reactant, 1 mole, 1 mole. So we should be rewriting this the same, 393.5. But for the carbon monoxide, as you can see, in the overall carbon monoxide is in the product, but in the step is in the reactant. So we should be reversing the enthalpy of this from negative to positive, and then add them. That results the enthalpy of the overall. We have got some of the ministerial exam questions. Let us solve the ministerial exam question as fast as possible, guys. For this question, the enthalpy of the reaction is given, including the enthalpy of the reaction equals, this is in the reactant side, so it should be positive 179.2. What's the enthalpy formation for calcium oxide? Formation for calcium oxide, this one. when the formation for CO2 and CaCO3 are given. Guys, that's simple. We should be writing delta H formation equations. Delta H is equal to a delta HF of all the products minus the reactants. How many products do we have? CaO with CO3. So CaO, we don't know CaO. Delta HF of the CaO. Multiply or add with the delta HF of CO2. This, of course, multiplied by the coefficients, minus delta HF of CaCO3. We know the delta HF of CO2. The coefficients are 1, that's why we do not count the coefficients. CO2, its delta HF is minus 393.5. Okay, we don't know the CaO, delta HF of CaO. That's a requirement. Equals, what's the delta H of the reaction? Of course, 179.2 minus the delta HF of the reactant, which is CaCO3. CaCO3, it has the enthalpy of formation of minus 1207.6. And then when we multiply this to that, it will be positive. Take that positive to the other side, and then the CaCO3 delta HF plus negative that number. Take the negative to the other side, it will be positive. So you will be calculating the delta HF of CaO, which is C is a correct answer, guys. I'm going to solve as short as possible because to not let the video to be long. Okay, in this reaction, calculate the enthalpy of reaction for the combustion of 2 mole of nitrogen monoxide, guys. Combustion of 2 mole of nitrogen monoxide. In the above equation, how many mole of nitrogen monoxide combusted, guys? Of course, there will be an arrow in between NO plus half oxygen form NO2, guys. 1 mole combusted. It said calculate the enthalpy of combustion for 2 moles, while the enthalpy of formation of NO and NO2 is given to us. So let us find the enthalpy of the reaction. The 0 is for oxygen. Enthalpy of NO2 is what? Combustion formation of NO2 is 33.2. Okay, this is the product, minus NO, it's 90.3. So this results something like 57. Let me calculate it. Minus 57, of course. 90.3 minus 33.2. It's 57.1. Minus 57.1. Minus 57.1 is for combustion of 1 mole of nitrogen monoxide. But it said 2 moles of nitrogen monoxide. That means multiply the reaction enthalpy by 2. So when you multiply by 2, you'll get minus 114.2. C is the correct answer. Okay, let us solve the next question. Minister exam question, guys. 23-24. The standard enthalpy for formation of liquid water is equal to this. How to write the standard enthalpy of formation? Of course, whenever it requires to write the standard enthalpy of a reaction or a compound, write that compound, 1 mole of the compound in product from the elements, guys. So H2O, the standard enthalpy of formation, 1 mole of H2O from H2 plus O2. To balance, do not change the coefficients of the H2O because this should be in formation form, because 1 mole of the compound should be formed from the elements, guys. As said, the standard enthalpy of formation of this has the enthalpy which is equals minus 286 kilojoule per mole. Okay. The enthalpy of reaction for combustion of 2 mole of hydrogen. How many hydrogen is combusted here? 1 mole. So for combustion of 2 mole, that means multiply the whole reaction by 2. 2 will be 2. Okay, the reaction will be 2, and then this will be 1. That will be 2. Combustion, that means simply multiply that value to the 2. You'll get the A is the correct answer, which is minus 572. The next question, calculate the standard enthalpy of formation for methane. So it requires to calculate this, guys, carbon plus 2H2. Calculate the enthalpy of formation for methane. Enthalpy of formation, 1 mole of compound must be formed from the elements. Okay, if the standard enthalpy of combustion enthalpy for hydrogen, carbon, methane is given to us. That means combust each of those guys. Carbon plus oxygen form CO2. Hydrogen plus oxygen form H2O. Of course, 1/2. And then methane plus oxygen form CO2 plus H2O. Okay. Okay, guys. Of course, 2 H2O and then the 2 oxygen to balance. The combustion of this one, H2, where is the H2, is minus 286. The carbon minus 394. And then minus 891. These are the enthalpies, delta HCs. But it needs the enthalpy of the above equation, guys. So simply use the Hess's law to solve this question. The carbon is in the reactant, here is in the reactant, 1 mole, 1 mole, so we write this amount the same. For the second one, hydrogen is in the reactant, hydrogen here is in the reactant, 2 moles in the main equation, but there 1 mole, so multiply this by 2. Of course, plus. The last one, it's the methane is in the product, here methane is in the reactant, 1 mole, 1 mole, so inverse it, the enthalpy, add them all together, reverse it as the reaction reverse it, that the sign reverse it, you'll get minus 75 kilojoules.